DNS. Okay, cool. So just before we go into this, I just want to help you understand DNS a little bit before we get going, because it is one of those core services on the internet, and when it doesn't work, applications and services, like we see, can and do fail. So I'll go through what DNS does. I'll talk about why it's structured the way that it is, how DNS gets to us, and how it answers to our queries, and I'll go through some of the limitations as well too. All right. So I'll try to give this a bit visual because, well, before I cover how DNS works and why it works in the specific way that it does, I just want you to be 100% sure about the functionality that DNS provides you. Because whenever you go off and access any websites, what you do is you type in the name of the website into your browser, for example, www.netflix.com. Now, you can imagine that that name, whatever.com, is then used to connect to the netflix.com servers and somehow then stream your movie or your TV show. But that's not really how any internet-based application really works. Simply put, we as humans, we like names. We like netflix.com because it's easy to remember. It's easy, it's netflix.com. Put it on a billboard. But, computers or servers or networks, they don't like it so much. All right, they like these IP addresses. So for me to communicate with Netflix, and again, any networking between me needs, what I need is I need the IP address of the netflix.com servers. So DNS does many different things conceptually, but at its core, it's like a big contacts database. DNS, in this context, what it does is it just maps IP addresses to domain names. It just binds them together. So whenever I go off and access netflix.com, I would have to ask a question. I would need to ask DNS for the IP address of netflix.com, which DNS would then return me back the answer, and then my device is able to use that returned IP address to connect over the internet to the Netflix servers. So I trust that makes sense. Like conceptually, the main piece of functionality within DNS provides is that it's just a huge database which converts IP addresses, DNS names, domain names like Netflix.com into IP addresses, which computers are better equipped for. Now, I hope that makes sense so far. Thumbs up if it does. At this point, it just sounds like a big database. So nothing too complex. And you might ask yourself, like, well, why not just have one big giant DNS server globally, or like a small collection of DNS servers locally? Like, we'll see that next. But for now, I just wanted to set the scene and make sure you really understand what functionality DNS provides. It is super duper important. It is critical to most of the large-scale failures that are caused by either DNS being failed or badly implemented DNS works. If you want to be effective at designing or implementing these cloud-based architectures, you have to use and understand DNS. Okay, so why don't we go ahead and actually understand, before the lookup process, a little bit about some of the reasons that it's structured the way that it is. Why do we need, first of all, loads of servers, not just one or just a handful of servers? Because believe it or not, there was a time and a place where it was just like that. If we go back to the infamous host.txt file, I give you a name. Sometime in the 80s, there was I can't remember his name. That's probably a bad search. In the 80s, there was one guy who used to do everything himself. By Paul Mokapetris. So Mr. Paul, we owe a lot to Mr. Paul, because Paul would single-handedly, one person was responsible for DNS. Up until 1983, it was just emailing Paul and saying, hey, Paul, can you tell me what the IP address is for such and such? And he would. And if you wanted to register your own webpage, he would accept your input and then add it to this infamous host.txt file on his computer. Yeah, the internet was a lot different back then. Up until the point where we need something a bit better. So kind of interesting. I think he's still alive. Yeah, he's alive. Yeah, cool story. Now, so one of the reasons why it was covered them, after 1983, the way that it was built, why do we need a lot of servers? Why is it that one pool isn't enough? I also want to introduce some key terms and then introduce the hierarchy afterwards. But right now, there are a few main problems with just having one DNS server in the world, or just a handful of smaller servers in the world, because it's important you understand the reasons, because then that'll help you understand why DNS is hierarchied, why it's architected the way that it is. First and foremost, obviously there's something of a risk problem. If everything was in one place, we give ourselves a single point of failure. The bigger the target, the bigger the problem. Okay, so obviously there's a risk, because a small group of bad actors or adversaries, they could easily just hack that single DNS infrastructure, and again, without too much effort, perhaps, it would then prevent it from servicing the genuine requests coming through. And that's something that we want to usually avoid for critical systems over the internet. Now, we also have a bit of a scaling problem, because almost anyone that uses the internet globally also uses DNS, which represents a massive growing load on the system. You see, a computer, like your computer, your phone, any device can only get so big. The fastest car in the world can only get so fast. Okay, there's a limit as to everything. If I say, what's the fastest animal in the world? What's the tallest building in the world? Whatever it is we're looking for, it's finite. Computers amongst them. So, well, what I'm describing here is vertical scaling, yes? Where you can scale one machine up and up and up and up, but there will be a point at which just no machine, not a single compute instance can deal with that much. There is just not sufficient capacity. So point being, what's the fastest car in the world? I can give you a very, very fast one, the Koenigsegg such and such, but I was looking for one that can do 311. So clearly, just one single machine isn't enough. I might have to then think about not just putting all my eggs in one basket. It can only get so big. If every request is being made against that one server or that small group of servers, again, no matter what information is being requested, that system cannot scale. So the question, how many different domains are there? Domains are domain names, like you go to a web address. Additionally, like DNS is, like we said, it's just a huge database. current estimates right now predict that there are over 763 million domains, such as Netflix.com, Gmail.com, Apple.com, Twitter.com. Those are all domains of a big, big pool of them, almost close to a billion nowadays. And again, each of these domains, each of these 763 million, might have many records behind it. Just one domain can have hundreds, if not thousands, or more records in each of those domains. And so what that represents is a huge data problem as we start to amount it all together. But then we need to consider, even if we had the world's biggest computer, it's not always going to stay the same. Like, this number will no doubt be out of touch 2024, 2025. So there will be updates to that data, as well as consistency issues as well. So all of that data also being accessed by everyone in the world, on a constant basis. You get the picture, okay? So having it all in one place was a bad idea. Hence, why we've addressed it this way. We've split the atom up by having or hosting more than one DNS server. I just kind of conceptually put here as 4 massive servers the size of South America. We can address the risk problem. I've turned that into green by creating more servers. We've reduced that single point of failure. We've eliminated that problem because each of these servers is now storing an exact copy of that same data. All of them are storing the same data. The more servers we have, the more load can be tolerated. We just saw evidence of this. The more can be tolerated against each of the servers. And, we eliminate a single point of failure, the less risk of attackers being able to take down the whole problem because you've got more of an attack surface. It's more servers. But it doesn't really help us with the scaling problem. Because if every single user, you and me, if everyone online, if every user of DNS communicates with any of these servers at random, it could be this, it could be that, it could be, round robin approach. That means that every single one of these servers needs to be aware of everything. Each of these servers needs to have the complete, wrong way around, sets of records. So I could talk to this one minute, I could talk to this one the next minute, I could talk to that one the next minute. Ergo, every single one of these servers needs to have all the data. It needs to have the complete DNS data set. So remember, that's that huge amount of data. It's a huge Goliath amount of data. So it's something that we still need to avoid. Ideally, we should have the ability to not store all the data collectively, but instead think about delegating control over certain parts of the DNS set to maybe say organizations so that those organizations can manage it. I'll take care of this bit, you take care of that bit, and so on. So I'll say, look, I'll take care of the UK domains. Alex, you can take care of the US domains. Also, but then you can, it goes on. .gov, .br for Brazil, .org, whatever it is, someone else can deal with those domains and so on. And so for that, then, if we all take care of a part of it, what we've got now is a bit of a hierarchy going on. So just before we talk about the hierarchy, there's a few key terms just to get this straight, okay? I just need you not to switch off for the timing, okay? Just to bullet point this. The first term I want to introduce is something that we call a DNS zone. A DNS zone. And this is the thing that you can think of as being that database. So we have Netflix.com, and that's the zone, okay? This is the zone. Inside of this zone, there are probably some DNS records, for example, www.netflix.com, as well as all the other ones as well, that live in part of that zone. So that zone, that DNS zone, obviously that's going to be stored on a computer, which is on a disk somewhere. And that is what we call, the thing that on the machine is going to be called a zone file. Okay, you with me? So on the machine itself, physically, it's called a zone file. Well, conceptually, really, this is a file which is storing that zone on a computer. So we said that there's a Netflix.com zone somewhere on the internet containing the Netflix.com zone and all the records that make it up. You with me so far? So we also have, to talk about the machines themselves, that's what we're going to call the name servers, or NS for short. Okay, and these are the DNS servers, which what they do is they host one or more of those zones. And it does, though, by storing one or more of those zone files. Yeah, these ones. So it's the name server for the Netflix.com zone, which can answer queries about the IP address of Netflix.com. It knows what that is. The name server is the machine that hosts it. All right. Now, next we have this term, not a concept so much as a label that we give called authoritative. And authoritative, that just means that for a given domain, this is the real deal. Okay, this is the real, the original, the genuine, to put it another way, the boss. Okay, it's the authority for this particular domain. It's responsible for that case. So some authority has to come from somewhere, and that's what we imbue as being authoritative. So there are several name servers in the world, and these name servers, if they are legit, if they're not fake, they're authoritative, and they can give us authoritative answers for www.netflix.com. So they can be trusted, is what I'm getting at, okay? And they're the single source of truth for that particular zone. Flip that on its head, and we have the opposite, which is the non-authoritative or the cached answer. So this is where a DNS server, it might cache a zone, it might do things in order to speed up, for performance reasons, it'll try to speed things up by caching information. And a cache, all that means is just to have some previously requested information, to hand, so that upon future requests, future pulls, it can serve that up a lot faster. So your router, your local service provider, for instance, that might be able to provide you a non-authoritative answer for whatever, DNS lookup for www.markoverse.co.uk. Great website, just FYI. Oh, sorry, NS lookup. It's not DNS lookup, it's name server lookup. And it does come back, so it hits me back with a non-authoritative answer. So It's able to retrieve the IP version 4 address, not the IP version 6 address. I don't have one, but because I've visited that webpage before, it's my webpage, but only because the name service can give me an authoritative answer itself, the ones that I've actually hosted it on. Okay, just my router has done things up to speed things up. So I just wanted to introduce those terms just so we can understand the architecture and the hierarchical system a little bit better. And don't worry, this is high level stuff. Okay, so the details are now over here. All right, so at this point we know a few things. At this point, we know why we talked about a few things. We talked about what DNS provides as a function. We said one DNS server bad. Okay, we know why having many DNS servers bad if they store the same monolithic set of data. We actually want to put things into different organizations. And you also know a little bit about some key terms as well. Okay, what I want to go through now is the hierarchy of the system in order to kind of appreciate the way that DNS actually works and looks. So using this architecture, we can split up that data that we talked about a second ago and then delegate the management of certain pieces of that data onto certain organizations. So we split the data up, which makes it easy to manage, and then also splits the load as well, which is nice. So that if you're querying Netflix.com, you generally you might not have to touch the infrastructure for Twitter.com or something else.com. You only touch the bits that you're interested in, not everything at once. For that, then, the hierarchy is often like a pyramid, sometimes like a tree. But just to go for the analogy of the tree, I stuck with the roots. And the roots, well, we start with the roots of the tree. So root servers. Root servers, these are the servers that host the root zone, which contains a list of all the top-level domains and the authoritative name. So what am I talking about? We start with the DNS root. And this is a zone, like any other part of DNS, it's also a zone, but this zone is hosted on DNS servers just like any other part of DNS. The reason it's got a crown on its head is because the root zone runs the DNS root servers. It's special because it's the point that every DNS client, every machine on Earth knows about and every machine on Earth trusts. It's where every DNS query starts. It's at the root, at the core of DNS. It always begins here. There are 13 root server IP addresses in the world which host the root zone. It's like those rings that were forged out of Mordor. That is the 6 for men, no, 9 for men, 6 for elves. I forget. Anyway, the IP addresses around the world, they're distributed geographically, a distributed network of physical servers located around the world, obviously to not cause a single point of failure, and that's managed again by various geographical locations operated by different organizations under the oversight of ICANN. So we're trying to decentralize the pots. We're trying to manage them by independent organizations. So no one person could take the internet offline, basically. So ICANN, the Internet Corporation for Assigned Numbers and Names and Numbers, so ICANN for short, they operate these, they're like the Ofcom of the internet, if there's such a thing. Yes, there is actually. It's called Ofcom. It's the, what's the word I'm looking for? The watchdog. The watchdog is, yeah. But they just manage the IP addresses, okay? They're the ones which host the actual root zone. Other ones as well, they include NASA and, let's have a look, I don't actually know. So who organizations who manage the 13 root servers? So University of Maryland, University of Southern Carolina, VeriSign, ICANN, these people, that people, NASA. Okay, anyway, these people, yeah. Cloudflare, they don't apparently. Anyway, that's that. So these people, all in all, independently host these 13 root servers. So to be clear, those 13 organizations, they manage the hardware, the computers, for the 13 root server IP addresses. Well, in reality, each of those 13 IP addresses represent many different computers. It's probably not one computer like we talked about. It's probably using a technique called multicast IP addressing. Okay, so one IP address will actually balance off to, say, many, yeah? This is a single stream related to multiple recipients simultaneously. So they have many computers in order to absorb that load, okay? But anyway, from a DNS's perspective, there are 13 root server IP addresses. And now the root zone here, remember this is just a database that's managed by IANA, the Internet Assigned Numbers Authority. So they're responsible for the contents of the root zone. So the management of the root zone, the management of the root service, which hosts the root zone is different. Now, as positionally aware as it is, it actually doesn't store that much information. What it does store is important to how DNS itself functions, but there really isn't that much data because the DNS root zone, it just contains high-level information on the top-level domains, the TLDs of DNS. Now, there are two types of TLDs. You got generic TLDs, which we all know and have used, like .com, .org, .edu, and you've also got country code-specific TLDs, which came about a bit later, like .uk, .br for Brazil, I do, whatever, okay? .tv, by the way. You know when you've been to a website with a .tv at the end of it? So Twitch, for example, .tv. Does anyone know where TV... It's actually country as well. It happens to sound like the word television. See, I'm at Twitch. Because it sounds like TV, television. Does anyone know? Like a curiosity? Comes from a teeny tiny little island called Tuvalu, which was famous some years ago because the Prime Minister appeared on national television warning us to stop having paper straws because his entire country was falling and sinking into the ocean. Yeah. So a very small residence, but they make a lot of, like a surprising amount of their GDP comes from selling the TLD rights to TV, because coincidentally, Tuvalu happened to get TV. So some silver lining there, I guess, but hey. Anyway, so IANA, the and ICANN as well, they have, so they delegate the management of those TLDs to organizations. And those organizations are called registries. Okay, like, for example, a US company called VeriSign. VeriSign are responsible for the .coms and the .nets. Okay, so they take care of those. So, okay, IANA manages that to the registries. I've got an example here. Yeah, that's what I'm referring to by these ones. So if IANA delegates management to VeriSign, like it says here, a US company called VeriSign, meaning VeriSign is a .com registry, and so in the root zone, in this tree to the left, there's going to be an entry in this machine for .com, and that points to, this arrow here, to the name servers which belong to VeriSign, who are responsible for that. So the .com, remember, .com is just one of many, many, many TLDs, top-level domains. There are other entries in the root zone as well for other TLDs, which could include .ru, .au, .br, .uk, and many more. Just because the root zone points to those top-level domains, that's what makes them authoritative. Yeah, that makes them the source of truth for those TLDs. That's the process where this root zone points down at the name servers which host the TLD zones. And that establishes now a chain of trust within DNS. So just to summarize, to be clear, the root zone here, that's pointing at the name servers which are hosting the TLD zones. These TLD zones are run by the registries who are themselves organizations that are running those top-level domains, TLDs. So, for example, we said VeriSign, one of many of these registries, they are operating and responsible for the name servers hosting the .com TLD zone. And the root zone here, it's going to have records for the .com TLD, which points at those name servers. So the .com zone, which again, just one of those many DNS zones, itself is going to contain some data, specifically high-level data about domains which fall inside of that .com TLD. Because no one goes to www.com, okay? You go to a domain, so you go to something like twitter.com, monco.com, blah, blah, blah.com. So we want to have some records for twitter.com and netflix.com, so records for the domains that exist within this .com zone, okay? So the TLD contains the high-level information on the domains within this. Netflix.com, in the case of our story here, again, this doesn't contain the detailed records within these domains. You know, for example, the www.netflix.com. So all the TLD contains is information on the domain itself. Specifically, if we look further downstream, in this example, if you follow it through, this contains then a set of records for Netflix.com, which, again, these records that are hosted in the TLD are going to point to the name servers, and these name servers finally are hosting the Netflix.com zone. Okay, because it falls part of that zone. It's obviously not the only one. It's also containing records for Zoom.com, which are pointing towards the name servers which host the zone at Twitter.com or Zoom.com, as well as any other records for every other domain within that .com TLD. Now, these name servers, because they're pointed at the layer from above, they're pointed at, okay, that means that these name servers are authoritative for the domains, you know, the zones that they themselves host. So the name servers for Zoom.com, the name servers for Netflix.com, they are authoritative for Netflix.com and Zoom.com because the Netflix.com entry in the .com TLD points at them. So we kind of, we pass authoritativeness by transitivity, if that makes sense. So we're officializing this, we're endorsing that particular record. We legitimize it. Now, these name servers, these NS name servers, they host the zone for a given domain. So for example, Netflix.com, which means that the servers, they host a zone file. And the zone file, that's the data, that stores the data for that zone. That's the thing that we're interested in. So at this high level, the zone contains records within www.netflix.com, which points ultimately at the set of IP addresses, the thing that we actually wanted to begin with. And because the zone and the zone files are on the same name servers, and because these name servers are authoritative for the domain, because it was allowed to be so upstream, and the zones and the zone files are also authoritative, that's what officializes this whole process end to end. Okay. Now, still high level, if you're with me so far, I just want you to understand that each layer of DNS, from the root, from the TLDs, from the domain name servers, we're doing it this way to only have a small part of the DNS database. So the root zone knows where the name servers for the .com zone is. The .com zone knows where the name servers for Netflix.com zone is. And the Netflix.com zone has records for the Netflix.com domain, which can actually finally answer the queries we're actually at last interested in. What's, you know, the Netflix.com zone, it actually has the records, the IP address or information we're kind of interested in, ultimately, the zone file. So this then is the hierarchy of DNS. And if you're with me so far, I'm going to go through the flow of that at a more technical level, okay? So how I want to go through the structure again. If it's still not clear, I just want to go through an example now of us making a query. So I just want to quickly again touch on the functionality that DNS brings, because if you abstract away from all the technical details for a second, what we think about then is having us as a person, as a human, or a device or a service, and we have a DNS name to hand. We need an IP address because that's what computers want. We want the IP address for the service behind this name. Okay, so in this example, we have www.netflix.com. What is the IP address or the set of IP addresses that we can connect to in order to finally access Netflix? So somewhere in the world, there is a DNS zone for Netflix.com, which has the answer that we want. That itself contains records which link www.netflix.com to probably a bunch of IP addresses, which is what we want, okay? The question is, how does that work? How do we find that zone? So DNS is the one-word answer, okay? That's what it does. It's the job of DNS to allow you to locate, this thing in the middle, to locate and get a query response from the authoritative zone, which hosts the DNS records you need. So you can query DNS, and you can be provided back with a response. It's a crystal ball that gives you an IP address. The IP address of the IP addresses, in this example, which provide you the services for Netflix.com, everything we talk about next from this point onwards is all part of the process to allow you to find the correct zone. Sure? So DNS is this middle thing here. DNS is just a globally distributed database containing lots and lots of different records around the world. And the function of DNS is to allow you to locate the specific zone, which can give you, finally, an authoritative answer. Okay, I trust that makes sense so far. So if we go through an example, if you step through this, all right, so again, imagine we're sitting at a computer, this is us, chilling, and we're querying Netflix.com. The first thing that's going to happen is we're going to check our local cache, our local DNS cache, and what's known as a hosts file, which is going to be on my local machine, my computer, my phone. Okay, so this host file is really just a static one-to-one mapping of names to IP addresses, and that actually overwrites DNS, because for performance reasons, it might have the answer, so it's checked first. Then the machine, and potentially the application using it, it might have some local DNS caching. DNS caching. We talked about what cache is. So it's to store a past, previously requested bit of information around. So upon future request, we can proceed and override that setting. It's a technique used. Okay, so that's something we can check before proceeding with a query, assuming that it's if it's a cache hit, if we found the answer, okay. But if it's a cache miss, if our local client isn't aware of the DNS name, which why would it be? For example, our website from a second ago, it only came online like a few seconds ago. Why would every computer on Earth be aware of that newly made EC2? So it's probably possible that my computer didn't know what the DNS name was that we're querying, which is why then we need to move on to the next part, which is why then we go off and we check in with a DNS resolver. A resolver is a type of DNS server, which is often running like on your home router or within your internet provider, and it will do the query on your behalf. It is the seeker hound, okay? It's your tracker. So we've sent the query off to the DNS resolver, and from this point onwards, it takes over. So from the resolver's point of view, and this is what a modern router does, it routes as well as other things too. So from a resolver, first, by the way, it also has a local cache. It's a server, it's part of your router, okay? But it also could be your internet service provider that performs this step. It has a local cache, which just like we saw, in order to speed up the DNS queries. And so if anyone has previously queried, www.netflix.com, marketverse.co.uk, as someone might do, it might be able to return you what we saw, a non-authoritative answer, because someone has been there before. It's just kept around that information in the cache, so it speeds things up. And remember, this is a non-authoritative answer because the only server which can actually give you that final authoritative answer is the one that's being pointed to at a given domain from the TLD zone of that domain. So since that resolver isn't aware, while it can cache the result, it will always return them as a non-authoritative at worst. In most cases, no one's going to care, but it's important to understand that distinction. Let's go for the full 9 yards. Okay, let's assume that there's no cached entry for Netflix.com. Well, in that case, the DNS resolver has to go out. It has to query, like we said, the root zone. We have to go to the top of the tree via one of those root servers. Now, every single DNS server in the world, so we have those IP addresses hard-coded into them. And this list is, again, is maintained by the operating system vendor or your browser vendor. So that DNS root, it won't be able to answer us because, well, this tree doesn't know where www.netflix.com is, but it can help us get one step closer. So the root zone, what it does is it contains top-level domain records. Okay, it contains records for example, .com, which is what we're interested in. Specifically, the name server records, which points you at the name servers for the .com TLD. So this is how trust is created, and this is how the root zone delegates control over the .com to VeriSign. So the root service will begin to return the details for the .com name servers, which isn't exactly what we're looking for because we're looking for Netflix after all, but it does bring us a step closer, which is good. And so at this point, we got close, but now that we have that information, at step 6, the resolver can now go off and query the .com name servers for Netflix.com. So assuming that Netflix.com, that domain it's been registered, the .com TLD, if it is such a thing, should and will contain entries for Netflix.com. So we'll go and check. And this is how VeriSign delegates control of Netflix.com domain when the domain is going to be registered with them. And so the .com name servers, while they can give the resolver the answer that it needs, they can help it move one step closer. And so the details then of the Netflix.com name servers, these NS records, they're going to be returned back. So did we get them? Well, now the resolver can move on because we don't have now that we have the actual IP. So we've now been able to query the actual zone name servers for Netflix.com. And because these name servers, the DNS name servers, the machines in the world that are authoritative for this domain, and because these machines host the zone and the associated zone files that make that domain, and because they're also trusted and pointed at by the .com TLD zone, that means that finally this is able to return back an authoritative result to the query back to our resolver, which is in the form of an IP address. So we bring that all the way back home. We store that in the cache if possible in order to give us a speed boost for the same queries in the future. And then we return that back through to the client, which was our machine. This is how DNS querying works. This is how it does. It's quicker if they cache this way, or it's even longer if you have to do the whole route. But give or take, it's electricity. It's a blink of an eye at most, or if it just needs to proceed to occur. But the key thing to keep in mind across this whole walking is that there's no single main server. We've not seen a single main server that has all the information for the reasons we've discussed before. Not even the root name servers, because we're trying to delegate the load. And this is key to how DNS operates. That every query, every single time we go off and ask the name server, it's a friend of a friend. It's trying to move us closer and closer and closer to the answer, because the DNS root servers, they don't have the full answer, but they do know a friend of a friend. They do give me the .com name servers. And the .com servers don't have the answer we're looking for, but they can know a friend of a friend. They give us the Netflix.com name servers. And those Netflix.com servers finally are the ones that are authoritative enough to give us that final authoritative result. So this process end to end is a query being asked and a resolution, DNS resolution. Okay, it's this whole process end to end. Okay, that's it from a high level. I trust that makes sense. And welcome, Kim. I just saw in the chat. Welcome, Kim. If that makes sense, at this point, do we have all the answers that we need? From a high level, at least. Okay, but technically, how does it work? Just to illustrate a more technical illustration here. What I've done is I've taken screenshots of this. So I did these queries. Again, we start from us. As all things, we start with the root zone. Okay, the top of the tree. And again, I've skipped a few of these steps because assuming that we don't already have that answer to hand, literally in the cache, we've gone to step 4. Okay, step 4 when our resolver is now going to query the root zone. So our root zone doesn't have all the information that we need, but it does know which name servers handle .com. It doesn't have the full answer, but it can lead us a step closer. So it's able to provide us with the .com name servers. It can give us this back. Okay, well, that's better than nothing. So these are a subset, A, B, C, D, of the name servers that, remember, were run by VeriSign. And VeriSign is that organization, that entity, which is managing the .com TLD. So these are the servers you're looking at, which host the .com zone file. Okay, well, now let's query them. Let's take that information and query the .com zone. Well, we can't get that answer from here directly. Remember, we're off the Netflix, but you know what it does know? It knows where the name servers, it knows which name servers are authoritative for Netflix.com. So it gives us that, okay? These then are the actual servers, Netflix. These are the ones that actually host the Netflix.com zone, which in other words is now authoritative, okay? It's the single source of truth, which this will give us the answer that we want, the one we want. So you with me? So in this case, if you look at it further, it doesn't look right either. So NS81, NS65, it's not right. Like, it's not an IP address. It's another DNS name. Damn it. This is something that we're going to call a C name record, a canonical name record. Okay, we'll talk about it another time. But what this means is that, it's for us to actually get the IP address, canonical name record, yeah. What we wanted is we have to follow the whole process again, through and through. Yes, I know. And yeah, that's right. Finally, like this end with another DNS name, which requires another query and another query. And one of the reasons that the application can perform badly is that if many DNS calls are going to be used within the application, if your application is very network intensive and network performance impacts this in a negative way, it's a thing to consider, okay? But all in all, this is how that process works end to end. This is how every DNS query works under your fingertips when you're trying to look up the IP address for a given DNS name, which is the architecture. This is the overall flow now for most, if not all, internet-based applications from a DNS perspective. And it's really a critical bit of information to understand fully, all right? Okay, last bits and bobs, just because I said we want to refresh it before the lab. I want to then cover how it is that we register ourselves with a domain, like what entities are going to be involved, what exactly is it that causes a DNS to get a new domain to be integrated within DNS. Because the process of us registering a domain includes a few key players, a few key entities. I mean, first of all, there's, of course, you're the key player, you're the person actually interested and registering the domain. But secondly, if you want to buy a domain, and I know because I need to for a project I'm doing, we checked a few places. We checked in something called the DNS registrar. And examples of DNS registrar might include, say, GoDaddy, Namecheap, Bluehost, and so forth, okay? Now, these are the people, okay, I'll come back to that. Next up is the DNS hosting provider, which again, examples include things like Amazon Route 53 and Cloudflare and EasyDNS and Namecheap and so on. And then finally, we have a third player called something, a TLD registry. So in the case of the .com TLD, we said, remember, we talked about that as being VeriSign, amongst which there was the University of Maryland and Berkeley and NASA and others as well. And finally, the .com TLD is going to be managed by that same entity. Again, one confusing element about this difference between the registrar and the DNS hosting provider, they are different things, okay, different functions. Because the registrar, this red house, it has one function. The registrar is there to let you purchase domains. It's a shop for domain names. And to allow this registrar, this red house, must then have a relationship with the TLD registry for many top-level domains. So you might use Hover, for example, to purchase a .com domain, and .io domain, or .org domain, or .uk domain, and so on. And so for each of these, they're going to communicate with a different TLD registry. So the high point is that the registrar, this red house, lets you register by the domain, okay? A DNS hosting provider, they let you operate the DNS name servers, which in turn host the DNS zones, and they allow you to manage the content of those zones. Now that's confusing again because sometimes some companies are only registrars, some companies are only DNS hosting providers, But some companies some services like Route 53 and Hover, they can do both, which is a little bit confusing. But again, we have AWS, and if you work within Route 53, the registered domains area of the console, that's going to be the domain registrar function. Okay, so if you work within the hosted zone function, that's the DNS hosting provided area, if you've seen that. Okay. Anyway, so if you go through the step number one is assuming the domain registration process, assuming that it's available to begin with, assuming that it actually is real and you can purchase it, is that we cough up and we pay for the domain via the domain registrar. So examples like that, we said GoDaddy and Namecheap and Route 53. If it's available, yoink, it's ours. Usually this is a 1 to 3 year lease, but there are variations on that. Okay. Second, this is at the point that we are now going to need a DNS zone for the domain that's going to be registered. So we want to register a domain, we need a zone, and this zone, it needs to be hosted, right? It needs to live somewhere on some DNS name servers. So if the DNS hosting provider, like Route 53, happens to be the same company as a registrar, that's easy. That's created and it's hosted automatically. But if it's a different company, you'll be asked for some of the name server information, like where the hosted zone already is. Because assuming if it exists because there's a zone for it. So let's get that information and then have to configure that separately. Okay, so I would have to do that and transfer that domain. Okay, so at this point, we have a domain that's being registered. We have a DNS zone that's ready to go because it's being hosted on some name servers. And then we have all the networking bits and bobs. All my duck is aligned on those name servers. Okay. Next up. Yeah. So the registrar that we're buying this through, that's going to communicate this with the registry for the TLD. So in the case of the .com, that's VeriSign for .link. I can't remember who it was, but that registry, assuming that everything's good and there's no red flags, they're going to add those details to the TLD zone. And then from this point onwards, that domain is live. Okay, for a domain to be live, the name servers which host the zone need to be pointed at from the relevant TLD zone, which in turn is pointed at from above, from the tree. So that if the zone ever changes, for example, if it's moved from a different name server or you change ownership or custody, then the entries in the TLD, so the name server records pointing at the name servers for this domain, they also need to be changed. And this is how you register a domain. That's how it's done. The key point really to understand is that there are two different roles. You've got the domain registrar, who registers the domain within the registry, and the hosting provider. Again, the hosting provider hosts the zone. Okay, they host the zone for the domain on servers called name servers. All right. So many companies end up doing both. Route 53 does both, but conceptually they're different. Which is what I wanted to say about that. Cool. All right. So that's what I wanted to say about this. That's what I wanted to cover about registering and setting up a domain, which at this point leads us to a good point. Hopefully we have all the things that we now need. If that's been a good recap of Route 53 and DNS, let's now try our challenge.